projections. All right, so as we've seen, addition combines two vectors to create a resultant vector. But what if instead we're given a vector and we need to find its component parts? So we can use vector projections to perform the opposite process, breaking down a vector into its components. So the magnitude of a vector projection is a scalar projection. For example, if a child is pulling the handle of a wagon at a 55-degree angle, we can use projections to determine how much of the force on the handle is actually moving the wagon forward. So it's sort of the shadow that we're creating of our handle in that direction. We return to this example and learn how to solve it after we see how to calculate projections. So let's get into our actual definition of projections. So the vector projection of V onto U is the vector labeled projection of V onto U. Right, so we see in this figure here. Let me go ahead and copy this figure into our notes. Right, so here's our vector U, and we're interested in the projection of V onto U. All right. So what do we know about this vector then? It has the same initial point as U and V. It has the same initial point as U and V. It's in the same direction as our vector U. And it represents the component of V that acts in the direction of U. All right, so if theta is the angle between U and V, so here's our theta, then by the properties of triangles, we can determine the magnitude. The length of the projection is going to be the magnitude of this vector, which is the magnitude of V times cosine by our properties of SOHCAHTOA. Let's go ahead and write that out. So if theta represents the angle between U and V, red maybe? You know what? Okay. Okay, so if theta represents the angle between U and V, then the length of our projection is the magnitude of the projection of V onto U, which is equal to the magnitude of V times cosine of the angle between them. So when we're expressing cosine of theta in terms of the dot product, we actually get this really nice result. So this is equal to the magnitude of V times the absolute value of the dot product of the vectors divided by the magnitude of the vectors. Right, so remember that this property comes from what we learned about the dot product way up here. So see where's the theorem that we're relating. Yes, we've seen these examples before. I think there was a name to this. So this was the rule that we're talking about. So you've got the dot product in absolute value divided by the magnitude of the vectors. Now keep in mind that we were multiplying by the magnitude of v in the first place, so that's going to cancel out for us. Where did it go? There we go. This is by the rule that says cosine of the angle equal to this. All right, so we have some stuff canceling out. And this tells us that the magnitude of the projection of v onto u is the absolute value of the dot product of the two vectors divided by the magnitude of u. So we can now multiply by a unit vector in the direction of u to get the projection of v onto u. So finally, projection of v onto u is equal to this expression times the unit vector in the direction of u. Okay. So this is just unit vector in the direction of u, giving us a final answer of u dot v divided by the magnitude of u squared times our vector u. So the length of this vector is also known as the scalar projection of v onto u, and it has a very particular notation. So the length of the projection is known as the scalar projection of v onto u. So this is denoted by count sub u of v. So the magnitude of the projection of v onto u is equal to the comp size of u of v, which is the absolute value of the dot product divided by the magnitude of u. So notice that whatever is our subscript turns out to be also our denominator. These are just little things you want to keep in mind in terms of trying to memorize these definitions. Let's go ahead and move on to an example.